All right, so last time we derived from this master assembly the front corner, excluding the shock and a few other sort of more detailed components, a model, which is over here, to begin designing this brake duct with the goal of scooping air in from the front, um, coming around the wheel, directing it over the brake rotor, and increasing our cooling capacity, both of the brake rotor and, of course, of the brake caliper in here. So I'm already done with that. Modeling is a rather long process, so I'm not going to record that at the moment. But I figured I would sort of step through the process here. So obviously, first thing first, right? I've brought in all of these components. Some of them I've named, some of them remain unnamed. These are usually like the smaller things, like some of these spacers holding the wheel in. But basically, I brought them all in and I've unlinked them from the master assembly. This is all basically built and on car, so it's not going to change in any way. There's no real reason to keep it fixed as a derive. If there was, I would have kept it, but this just makes it a little bit simpler and faster to update, etc. Um, so the first thing really I did, I made a construction plane and an axis where I could do my first few sketches. And really, my first sketch described the maximum areas, kind of like how I talked about in my last video. Um, we don't want this going too low. We don't want it really going too high. There's pretty minimal gains up here, and it can't come too far out because you don't want to run into the wheel here. And then some clearance roughly around the caliper. So this is the sort of base sketch. Now you could do this slightly more efficiently with regards to the surface modeling I'm about to show, but really for the complexity here, this makes it kind of easy. So basically I've got this rough footprint. The next sketch, which has quite a bit of excess projected material. I wasn't quite sure how much I was going to need of this, so I just intersected everything, and it looks a bit messy, but um, most of it is unnecessary, but technically doesn't affect the drawing. So what I've done here is I've basically given a max envelope, so a max depth inwards from my mounting point. Don't want it or need it too close to the rotor, but it needs to come inwards so that anything, basically where the brake duct ends is either directly against the rotor or the upright is going to push it into the rotor there. So we have an inward set, an outward set here where we're grabbing it 2 inches out. Um, that's our air away from the tire roughly. A little bit less. It's more like 1.5 inches. This may get bumped out in further iterations, but that's what I was hitting for now because this is pretty low profile and I don't want to go too extreme my first try. And then I've just got some nice radiuses, and so this is sort of my center profile here. Um, Once again, this is built off this main base sketch. Then the next two sketches are pretty simple. I did these 70-degree planes at angles along this top and bottom edge. This is just so that the brake duct has this natural slope inwards as we start. Um, and then the sketch up here, pretty simple. Which section is, there we go. Pretty simple. Once again, just trying to make sure we dodge the rim, using relatively similar angles and radiuses as were used down here. I'm not projecting anything up because it doesn't really match up at all. Um, but yeah, once again, pretty similar. And then the exact same concept for the bottom sketch down here. And that really describes our three main surfaces that we need. Um, and this is already enough to start our loft. So if we go over to the loft, uh, I said surface modeling. I did it first with surfaces and then realized what I needed was actually going to be easier with a solid loft. So that's my bad. But that's these three profiles listed here, right? Now you'll see that I have rails. If I were to go in here and remove these rails, This would be purely what the surfaces get us. So if we remove the rails, hide the sketches, you can see that this just kind of sweeps along as you would imagine. Our side profile, this isn't the most desirable curve. And our front, it's all right, actually. It's pretty decent. So the first thing I did, and this is how I found is the easiest way to avoid your, you know, profile or rail doesn't intersect the profile issues, is to actually, when you create your sketch, your profile, before you do anything, use the intersect tool on your baseline sketches, so these surface sketches, and you click anything that's going to intersect your plane. So in this case, really only this line, and it's already been intersected at this point here. But you get this projected point that you then must make all your lines run through. So if I were to, my bad, that's the wrong line. So if I were to delete this, you can see this projected point down here coming off of this portion of this bottom surface. And so that's required for you to, have your rail be used effectively. So that's that back rail. So if you look at just using this rearmost rail, it works quite good, but you'll notice it leaves this crease beyond where I want around the corner. It's kind of undesirable. It doesn't look great, and you know this end piece having a crease in it is just not what I want. So taking that, I then make a second rail. So going back into here, once again, I'm just using an offset plane at an angle, making sure it can still intersect every profile, and then I sketch it from the front. I just sketch a nice arc. So now you can see this front plane is doing pretty well. The shape in this direction is correct, but if you look at it from the side, yeah, it's just kind of ugly. It's not it's not looking good, right? Where this profile and this profile ends, you sort of have this straight line, and then the third profile pulls it forward, but it's just a weird geometry. And so this third rail pulls everything forward and decides or defines this forwards curve here. Realistically, if I wanted it to be a little bit more aesthetic, I could probably look at pulling this curve in, and that may come in a future iteration if I find that the middle is building too much of a pressure wall or, it's not as efficient. But for now, um, this shape right here, I'm going to consider to be good enough. So the key moving on from this is we have a base shape. Um, After that, what I did um, is I found sort of the main geometries that actually intersect my area here, and really primarily that's just this brake caliper. That's the only thing that's in the way. And so I made a primitive um, that I can subtract from my brake duct just to make sure that I don't have any interference in that regard. I put an offset surface out here, and I drew I slightly trimmed the back of this brake duct because in my initial iteration, um, you can see it stuck through the back, and so I had this weird artifact where when I subtracted, there was kind of a hole in the duct here, and I was worried that air was just going to go out and past the upright instead of inwards. So I removed a little bit of extra from the inside here. So I still have clearance for all the mounting points on the inside. So I still have clearance for these mounting points, but I don't have any worries about the air escaping past. The next technique I used, this one's a little bit silly. There is, once again, a bit of a better way to do this, but this was the most efficient. Um, what I did was I made a duplicate. So there's actually two of these surfaces here. Um, they're identical, they're copied. It's just two bodies stacked on top of each other. And then I shelled the main body. So now I have this main body and I have a body that fits directly inside of it down here. I combined them so that now they don't overlap anymore, right? I have an outer body and I have an inner body right here. And the reason for this is I want to make fins, but cutting them out all individually, especially against this complex shape, is rather difficult. So instead what I did is I made a sketch where I had all my fins along with my mounting point holes, because those were quite important. That ended up being a bit of an afterthought I had to add later, but fortunately it was parametric enough I was able to do so. So I added all those, and then I extruded these through. This is an intersect feature, so it only keeps the extrusion intersected with the selected bodies. So in this case, the only body I have selected is that inner portion that I had earlier. And so that leaves all these nice fins that are perfectly clearanced as I want them to be. And they fit perfectly inside here. So when we step to the next feature, we can see that they join perfectly with this outer case, right? That directs the main majority of the airflow. After that, pretty easy subtraction of this, clearance box here. A couple of fillets to make everything look nice. And then really that's the majority of this fin taken care of. The rest of the operations here deal with properly inserting all these holes for the bolts. This could be done in less operations, but this doesn't need to be very well parametrically controlled because it's at the end of the part, and also not very variable. I know the length of bolts we ordered, and it is what it is. A few more features here. Um, and then I did some simplification. That's what the rest of these combinations are. So instead of having these as separate parts, when I move them to CFD, right, I don't want too many separate components. It's much easier to just have them as larger components. So I did some combination, I did some naming. And then the last thing here is I created a tire that was primitive. So the old tire has all these knobs on it. I'm not manually rotating this tire. I'm not deforming the mesh, doing anything like an overset mesh in CFD. So these knobs really aren't going to do me much good. The tire's not of that much interest to me, to be honest. I'm mostly interested in how the air comes off the sidewall. So the interest of being able to rotate the tire surface and deal with that, I just made a primitive revolution of said tire. So to put the rim back in, it's the exact same dimensions, it's just removing the knobs and any surface unevenness. So you can see that's how it fits together. And then this last portion here really is just creating a fluid volume right here. I prefer to do this in CAD most of the time rather than CFD. You can get some interesting artifacts if you do it in CFD. And I've just found I'm much more comfortable with the CAD softwares in perfectly defining and keeping all of this parametric, right? Your initial box size and all the rest in CAD as opposed to doing it in CFD. It can be a bit more flexible if you do it in CFD because you can have, you subtract features and update it. But for my workflow, this just seems to be more reliable for me. So once again, just removing, doing a combined feature here, uh, to keep these from anything from overlapping. I'm basically subtracting all these, and then this subtracts some of the extra entities, like for example, all the volume inside the control arm tubes. That doesn't actually need to be modeled, so there's no reason for me to keep, that in the simulation. That would just either be an extra component that I wouldn't want to mesh, or it would mess with my fluid volume, and so it's just easier to ignore it. So yeah, if I head over to my notes here, surface modeling theory, there's a really good overview that Onshape made. I won't pull it up here, but I can link it under the video. This is honestly, and I found this in like the last 2 days, by far the most comprehensive overview I found. maybe I'm blind and I haven't looked in the right places, but you know, it, I found it and I like it. It's got a lot of good images on there. The first time I really understood, some of these tangency constraints where you're given G2, how the analysis works, all that kind of stuff. Like that's really the first time I've understood how all this is actually supposed to work, and where the controls for that are. So I have a few notes here, right? For surface modeling, got to think in cross sections. Your rails must intersect your profiles or your curves. And then tangency issues are probably going to be your most common ones, unless you have some intersection problems because you didn't project your lines correctly. But yeah, so that's the design considered. So for some of the analysis, we go back to Fusion, you'll notice that uh, these brake ducts actually lie at a 6-degree angle. Part of that is that's basically what our inclination here is. If I hold this straight, you can see that the upright is slightly tilted back, so that puts it at a rough, nice 90-degree angle. The other one is, even though I did an initial simulation with the tire rotating and I couldn't detect a significant influence of the tire dragging air down into the ducts, so basically, the tire rotates forward, there's some law of the wall, some no slip condition along this tire, which is going to be dragging air with it and creating some turbulence and some vortices. Initially, I had these set upwards at about a 20-degree angle. That was way too much. I should have guessed that it wasn't going to be that big of an effect, but I think 6 degrees. Aesthetically it's pleasing, and it seems that that's probably pretty close. Obviously, subject to change. Um, the next concern was some of our boundary conditions. So if we bring up the fluid volume, obviously this is going to be the inlet where we bring our fluid in. So that's the fluid's going to flow across the model. We're going to have an outlet right here where all the air goes out. Everything else, these sides, I'm just going to set as basically free stream, so no boundaries on them. Um, I mean, it is a boundary of the fluid, but you're not going to be generating turbulence off of it. They're they're planes and walls with a slip condition on them, so you don't generate a surface layer. And then this is going to be approximating the road. This is going to be moving basically at the speed of the air or the car, because from the reference point of the brake duct, the road is moving. So you want to make sure that your tire and your road are both moving at the speed your car is moving through the air. Because otherwise you can build a boundary layer. It's probably not particularly affecting the brake duct here, but if I was interested in downstream stuff, downstream of the tire, or interactions near the ground, like if I was putting, some aero on the Baja car for some reason, I'd very much be interested in that. So internally, the CV is going to be a rotating condition. The tire I've already mentioned. The entire rim is going to be a rotating condition, and these are just going to be stationary because, once again, overset mesh is a bit beyond what I want to deal with. And then lastly, the surfaces of the brake rotor are going to have a tangential velocity applied to them, but the physical brake rotor body, like the solid body, won't be rotating. Um, I don't think I could get the simulation to resolve the slats anyways, and so I'm just going to use the full model here for heat transfer and for maintaining how much heat there actually is in this rotor. Um, so it heats accurately, right? We have the correct amount of mass, but I'm not going to bother trying to rotate that. So hopefully that's a valid simplification. Um, and yeah, that's pretty much it. You can see airflow should go nicely through here. May want to trim this bottom one. It may not be very effective with this smaller inlet here, but the rest of these should have pretty clear flow. I'm hoping that these mounting points don't obstruct anything significantly, but I believe we should have decent flow in, even behind the caliper here, now that the mount has this pockets in it. And yeah, I'm hoping this yields some good results when we look at and analyze the results of the CFD next time.